Good afternoon, everybody. I want to welcome you
Yeah, there's
to
always room for improvement.
the next celebration of faculty career colloquium. It is a very brief introduction. This is an outgrowth of the strategic planning process that was done in the college a couple of years ago. And the idea was that we would have full professors, after they become full professors, once every 7 years, give a colloquium, and this would be a chance to tell their colleagues what they're doing, kind of think about what they accomplished in the last 7 years, and do some planning for the next 7 years. So one of the components of this is, besides the colloquium, our faculty who do this have a chance to meet with the dean and the department head to talk about the planning and the next 7 years, and be able to take advantage of potential resources or what they want, what they need to be able to accomplish the things they want to accomplish. And so today it gives me great pleasure to introduce Wayne Chen, who is a professor in the School of Aeronautics, Astronautics, and Materials Engineering. Wayne got his PhD in '95 from Caltech, and we were very happy to recruit him to Purdue in 2005. And as you all know, our College of Engineering strategic plan talks a lot about impact. In fact, our tagline for the college is Think Impact, and guess what? Wayne is an expert on impact, and he's going to tell us all about impact. Thank you, Wayne.
Thank you very much. Thanks for coming. Yeah, actually, when I was preparing for this talk, I missed the timeline 7 years. So I had the one advice is that once I give this talk, I'm eligible for retirement. So I think I'm going to do a progress report, but the timeline goes much farther back.
Absolutely.
So I'll pretty much talk about my education background, the research I've been doing so far, and the plan for the future. Of course, future will change, but this is actually at least on the plan. Well, I grew up in China. This is more than 7 years ago. Got into aeronautics by building model airplanes. So when I was a kid, building model airplanes, getting into aeronautics. All my degrees are in aeronautics. So the earlier times, I think that's over 30 years ago, I got bachelor's from Beihang University. It was building look like this, and nowadays it look like this. So this is where actually I got my undergrad, but actually I'm running the lab classes next semester here. When I was doing my undergrad 35 years there, the lab equipment is actually more than we have here now. So it's kind of interesting contrast. But then I went to get my PhD. Of course, Caltech is nothing changed. It's the same old Caltech. And of course, if you talk about equipment, what equipment? If you need something, build your own. So that's my last degree from. It's '95. So when I got into Beihang, that was the top ranking aero university in China. I think it still is today. And when I got my PhD there, Caltech's aeronautics is a #1 ranking program in the country. And I think it got back to that spot now. Well, there was a gap, right? So I don't think I'm that dumb. That took me 10 years to get my PhD. So I took some time off to have some fun. Spent 3 years, designed small aircraft, build them, and flew them. So I get pretty good when building these airships. I was pretty good at tailor. So if you have a sewing machine, you sew 2 pieces of clothes for 100 foot long. And if you don't do carefully, by the end of one piece can be 5 foot longer than the other one. So, but we use this vehicle basically to pull the electrical line from the first ever Yangtze River Dam to the area the electricity need to go to through the very tortuous mountains. We get lines from air through. So we did some real work. But then after a while, I think, well, these are too small airplanes. I built model airplanes. This is just a bit bigger than the model airplanes. I want to build something bigger. So that's my next phase. I was a part of this jumbo jet airplane design team of 7,000 engineers. And it turns out actually it's not as much fun as I expected. You get confined to a very small area. So, but I was set by the runway when this airplane took off for the first time. And it was a very exciting moment as an aerospace engineer. Very satisfying moment. But after that, it started getting boring. So I was asked to be transferred to the R&D department. And they said, you're just a production line engineer. You probably need to show an advanced degree from this country. I said, okay, I'm still young, I'll show you one. So that's when I got back to grad school and got my PhD from Caltech. The problem is, while I was in Caltech, the company became Boeing. So, and R&D department is just completely gone. It's just a department in the Cal State Long Beach. So now I cannot do. Then you go teach. So I get a job at the University of Arizona. This is where I start my teaching career. It's a spectacular place, very beautiful. So I figured I'll be retiring there. But then obviously I'm here, I'll tell you why. Weather is one of the factors. While I was there, I spent a couple of summers at the Army Research Lab, working on things that they have a flying dart hit on a ceramic tile. And actually, scientifically, it's pretty much fun. We had one of the papers coming out is on the American Ceramic Society journal cover. We deal with the ceramic impact failure. And recently, Army Research Lab changed their logo. I told them, keep that. I like the color. And Byron Pipes is their scientific advisory board chair. So I think that's probably why they changed the logo to this color. Now I'm here. So now I can talk a little bit more about coming here, start first year as an associate professor, then became professor next year. So it's been 8 years as a full professor. So I'm 1 year overdue. The 7 year was the first time I heard about this. I thought I was one of the younger guys talk about the career, but I'm already actually overdue. I was very fortunate to get very well treated here. So in the almost first 5 years, I was selected as university faculty scholar and has some little money to do whatever I want to do. Then, of course, I'm trying hard to bring some money in. So if you're in the research side, you know that this means I'm keeping bringing some healthy amount of money to do the fun stuff that I'm going to show you later. So as a result, I'm very proud to get an award named after the most respected colleague of mine in my school. Then, of course, as you get a bit older, you need to do some service. So I'm running the grad program for Aero School for the last 2 years. On the outside, became fellow of American Society for Mechanical Engineers, and recently Society for Experimental Mechanics. And I was an associate fellow for American Institute of Aeronautics and Astronautics during my Purdue time. And also I do various services in the society. I've been the member of the United States National Committee on Theoretical and Applied Mechanics for the last 8 years. This is actually my last year. I'm going to get rotated out. I represent society, the American Institute of Aeronautics and Astronautics in the National Committee. And I'm an associate editor for Journal of Applied Mechanics. I'm in charge of all the impact mechanics papers. So why I left Arizona and loved this weather. there are two major reasons. This is the one. We get very high quality students here. So this is my first batch of students. I came here in January 2005. So there are two assistant professors. One's actually coming in here and is being visiting me. Yeah, I think this guy has a trouble spending his money. He's been the assistant professor for 2 years and got over $2 million. So he's now bumping his head on the wall. And the next younger ones are growing up. So this one got the first place in the international student paper competition last year in a societal competition. And this actually just made national news a few days ago. So the National Department of Justice called for a national challenge on the body armor, police body armor evaluation. And it's open to everyone. You can be national lab, industry, research institute. And eventually, my students beat out everyone to win the final contest. So that was just announced. So it is a very satisfying experience when you have an opportunity to work with the hardest working people that are also brightest. So they're very creative. And of course, second, the factor is we have a group of outstanding colleagues. Almost anything you want, you need a question about anything in engineering, you can find someone to talk to. And it's easy to work with people. I work with colleagues I've never met, write giant proposals, and get funded. Also, another main issue that I left Arizona is I'm pretty much grow out of capacity. My lab was way overcrowded. So at that time, Purdue was expanding and their lab spaces. So this is the basement of Bowen Lab, and it's a perfect place. You can make big noise without getting noticed. So you can build big guns and actually play down there. So I actually told my students in undergrad class, I was teaching structural analysis. So I told them, your professor, when he's this tall, he likes two things, guns, airplanes. So as a little boy, what you're going to expect, right? So now the professor's over 50 years old. I'm teaching you guys airplane design. Play with bigger and bigger guns, right? Look at the size. And then a rifle looks like a toy inside there, right? So it's a lot more fun and get paid. So it's a career that you really cannot complain. It's so nice. All right. So what do we do with all these tools? I have good toys with smart people. Now we need to do some scientific work. So the area I'm working in, this is an axis that tells you how fast things are deforming. So most of the properties you're going to find from books are in this region. Once material deforms faster at a higher rate, you don't get the properties on the books. So that's actually my lifeline. We characterize impact response of materials at high rates. And sometimes we do obvious impact. Sometimes it's not that obvious, the cell phone drop. Actually, I once characterized the shock isolating material for a cell phone company. And later I noticed that that was over 10 years or 15 years ago probably. Then later I noticed the cell phone company made their advertisement. Other people's cell phone dropped to a concrete floor, the cell phone shatters. Their cell phone dropped to the concrete floor, the concrete shatters. Say, I know what that the capacity. So this is the area I'm basically work with people with applications in impact situations and ballistic impact or the crash or drop situation. How do we work on this? This is my basic tool. So I want to deform the specimen, a sample, at least hammer blowing rates. You can break a piece of material, but just by hammer, you put it on the table, you break it, right? It's not a big issue. The issue is we're a scientific lab. We need to make things quantitative. So how do you make things quantitative? What we do is we put an elastic rod in front of the sample and elastic rod behind sample. So the hammer will hit the sample through the rod. You generate elastic stress waves that load the sample. Some of the wave will reflect back, some of the wave will go through. So this is the same phenomena as if you stand by a pound, you throw a piece of rock in the pound, there will be a wave propagating to your feet. If you throw a big piece of rock, the wave is higher. So the wave carries the information about some event occur from a distance. So this is a class actually I teach at the graduate level. How do you analyze these waves using this phenomena? So by these tools, now we can make things quantitative. I can measure the strains on the surface of the rod associated with the wave that coming in called incident, reflect back called reflect waves, and transmit it, that the wave goes to the other side. With these three pieces of information I measure in the lab, I can find the stress strain curve of the sample I'm hitting. So now still I'm hammer blowing rates, but I get quantitative information out. So you hit it different ways, you get a family of these curves that numerical people can use to embed into as models into their codes to simulate structure response. So that's pretty much the path where we fit in. So with that principle, we have quite a few different bars it shows up. In the lab, it look very differently. So this is a very small one. We actually used to pull 3 micrometer diameter spider silk. We're trying to see how that breaks. There's a lot of things you can learn from spiders. They've been around for 400 million years. So this is actually was a paper that my student got first place in the student paper competition. We also have bigger ones that we're going to characterize high strength concrete. If you want to make this building blast resistant, we characterize those materials. We have a bar that can apply pressure on the sample equivalent to 10 miles underground. It's a very high pressure, then you can do axial impact. Or you can have a very long bar. This is probably the longest in this country at least. The issue with these devices is that everybody understands principles, but there's no standard that guides how to conduct these experiments, because these are not trivial experiments actually. So that's where I spent my first 15 years or so of my career, trying to ensure that this material deformed under the conditions that we wanted to deform, and we can explain it clearly. So here's an example. I was measuring the stress strain curves. If I have a piece of stainless steel, the strain stress, if you're in the mechanics, you plot basically the load deformation history. But I can plot the load from the front end. Remember, my sample has 2 ends. Once the front get hit on the back end is transmit load out. If I measured the force from front end or the back end, which is called 2-wave, 1-wave, 2 waves front end, 1 waves back end, you see they reasonably overlap each other. So the load in the sample is reasonably evenly distributed. Front end, back end is very similar. If I change the sample into a lead, still metal, this would be the curve from the back end of the load history, the dark one, and this would be the stress strain curve from the front end load history. Now we're going to run into problems. How are you going to explain this? What you're going to report to your sponsor, that the 2 ends are so different. And this is not as challenging because lead is still much harder than later the material I show you. They're in much, much softer material, so things get much more challenging. So I'm measuring stress strain curves. The stress may be wrong if your sample is not as hard. And if you look at strain, if a sample is soft, do I talk about strain here or here? They're quite different. So if for soft materials, if we don't pay enough attention to what we're doing, you mess up the load measurement, mess up the deformation measurement. You don't get anything valid. So what do? You need to look back what the tools we have. We have two skinny rods that sandwich it with a sample. These rods are much less stiff compared to your static material testing machine. So the sample response to your loading is an integral part of the experimental design. In a static machine, you set the machine, you put a piece of rubber or a piece of glass. The machine will run the same way. It has its own closed loop control system. In the high rate impact machine, you hit the same way. If I have a hammer, you hit a piece of rubber or hit a piece of glass. You don't expect the sample is going to deform the same way. So the experiment to be designed very carefully. You have to control the way how you hit it. And I don't have many things to control. It's only two rods. So it's how you hit it. You have to push the material initially at rest. This is common for all dynamic experiments. The sample initially is at rest, then you want to deform at high rate, you have an acceleration process. So the whole trick is how do you control the acceleration? You're going to push the material in a way that it gets high speed deformation before any failure occurs. So what we do is called pulse shaping. We will put, this is the hammer, and this is the rod in front of the sample. Instead of direct impact, where all the momentum from the rod can transmit into the incident bar, we will put some momentum faucet, little deformable materials, so not all the momentum can get in there. You control the way how to get in there. So you're going to control how you hit the sample. And of course, you need to get things quantitative, but that's a lot of things while you have graduate students. So you figure this out, make it into the program. Yeah, and basically we can show that we can predict what the real response would be. So how I need to load the sample, I can make the pulse shaper in the computer before sent to the machine shop, which you're going to make you wait for 2 months to give you any piece, right? So this is a very effective tool. Once you have these, we have this quantitatively set up, and now we can do the experiment. The impact loading history will be very different, but that would take an expert in impact mechanics to understand why this is the very good. But we also verify to measure whether the two sides of the sample has the same loading history. And we also have high-speed camera to show that the samples indeed deform uniformly. So this is one example. If you have a sample soft, you need to take a series of measures to make sure that you obtain valid result. On the other hand, if a sample is brittle, you have other set of problems that the sample breaks very early. So you need to develop many other techniques. So for the soft part, we apply the techniques we developed and actually worked on the soldier protection program. If you design body armor, and if you use computer to evaluate the effectiveness of armor, you need to know the material behind the armor, how they respond to impact. So it's everything you can do, from muscles to lungs, liver, kidney, skin. So we did lots of these, tendon. And even more challenging, this is for the traumatic brain injury issue. So we characterize the brain tissues. And we did a lot more. So as I mentioned, this is a summary of more than the past 7 years. So we did quite a bit more, and we also become fairly well known in the field. And I actually taught a short course in the society annual meeting show people how to do experiments on different materials. Then we got a lot of questions. How do you do this? How do you do this? Eventually, we published a book, summarize the different methodologies we use to characterize different materials. And this is still the only book in the field. And if you go to an impact mechanics lab, there's a good chance you'll find a book there. It's a fairly well accepted book. So this effort's still moving on. We have different requests to characterize very challenging materials. But on the other side, we still, my interest is getting into a different area. I'm also a materials professor, right? So I'm interested in how these things breaks. I can measure the stress strain curves, that's one thing. And I also want to see how they break. Some of this behavior you can see from surface. For example, this is an aluminum sample. So if you're in an undergraduate materials testing lab, you have an aluminum sample, you compress it, the sample would drum out. And I was requested by a group that they do very high deformation analysis. So they want the sample to deform to very high strain without drum. So you see this is the sample start with a flat surface, even to very, very high strains. The edge remains straight. It never drummed down. And this is actually a nice piece of the work, but this is what we actually want to learn from surface. But some other situations, you start want to see what's inside. This is a foam experiment, and you see dust comes out, and you want to see what actually happened inside. This is a tank armor ceramic. This is probably the third hardest material in the world behind diamond. So you put on the surface of a tank to resist the ballistic impact. So, of course, we can use high-speed camera to look at how this thing disintegrate. But where did the damage initiate? If it's initiated from inside or on the back side, how do I see it? So this is a new challenge we've been dealing with more recently. We look back again, the limitations of these experiments we've been conducting over the last 15 years. That we measure the mechanical properties on the average sense, average over the sample volume. If there's a local deformation inside the sample, the technique is not sensitive to it. Also, if the sample is opaque, you cannot see the damage process inside the sample. So how do you see through things that's opaque? X-ray. So we were trying to use X-ray. And now, of course, this is not going to be the dental X-ray strength because the phenomena is fast. I need a high-speed camera to record in the failure process. So if your dentist is going to take a few seconds to take an X-ray of your tooth, a few seconds I will run a few thousand experiments. So my X-ray needs to be much stronger. There are two ways to make X-ray very strong. One is the flash X-ray. They are nanosecond, very strong X-ray, but that's only one flash. If you want to have a continuous high-speed image of X-rays, you need to have a very strong continuous X-ray source. The second part is that when you deal with materials, X-ray typically give you a radiogram. If you have a hand, you see the bones clearly. The rest of it is just cloud. You don't really see much. But that's because the density of the bone and the rest of the tissue is drastic. If you have material, even with two faces inside, the density difference is not that much. So you need to find ways to increase the contrast. So these are the two issues we need to overcome, the intensity and the contrast. So how do we overcome the intensity? This is the lab that we're actually running. Luckily, it's only about 2.5 hour drive from here. It's in Argonne, outside Chicago. So the electrons running inside the storage ring can be extracted out, and you force the electrons to go to zigzag motions called an undulator. Then every time you're forced to turn, you shoot out X-ray. You collect the X-ray and characterize the sample. For the increase in the contrast, we don't really put our image plane right next to the sample as you have in your dentist office. We take images away from the sample, give it some distance. So if X-ray goes through two faces of the materials, as they propagate, the face is going to interfere with each other. After distance, you see a little bit thickness of the interface that initially has a zero thickness. And that's how you increase the contrast. And I'll show you an example that we can see mechanisms inside very soft tissues that typically you can see a cloud only in a medical radiograph. All right, so that's the idea. Then you need some smart people because there's a lot of coordination you need to do. This is my loading bar. This is a sample. There's a load cell behind it. So you need to make sure that X-ray comes while sample is being stress wave loaded. X-ray is so strong, you cannot allow it to come early, otherwise burn up your sample. And you have to shut it off right after loading. Otherwise, it burns everything along its path. So you need to have the coordination with all the shutters. Then when X-ray sees through the sample, you cannot really manipulate it with X-ray much, except the pure single crystal silicon. So we actually converted the X-ray into visible light with a scintillator. So you can manipulate it, you can reflect it, you can magnify it, and it recorded by high-speed camera. And this high-speed camera also needs to be phase-locked with the electron bunches coming from the rain. So that's another level of synchronization. And when you have a group of very smart students, we construct all these from the concept that we want to do these experiments to we actually work in the lab, in the Argonne National Lab in 3 months. So everything's constructed, remotely controlled, and pass the Argonne safety inspection. So then we can do something fun. So we can use the tool to do science. I'll give you a few examples of the science that we do there. This one, we put 2 sand grains next to each other and use the bar to impact the grain and look at how the grain break. So that's a very fundamental mechanics issue. And we can measure the loading history, that as the grain breaks, the first one break, then reload back, the second one break at a higher load. If you fill the tube with water, then the loading history is a little different, but I'm not going to talk about this wet issue. We're going to show you the dry grain results. So here, 2 sand grains get pushed horizontally, and you're going to see surface damage. This is the image you're shown is just through the thickness. So on the surface, you see that that's the initially surface damage, and the one side developed much faster in damage. Eventually, this side explode, but the other side, see the damage stop. So if 2 sand grains in each other, when they fail, one would explode, and the other one will survive. And we did quite a lot of them. So the previous one, the left grain exploded. This one, the right grain exploded. So there's no other failure mode, like one grain is going to split into 2 halves. It's always explode. Once it exploded, then it's unloaded, the next one will survive. How about 3? So you'll see this one exploded, then this one. The middle one actually survived. You can see still there. So you can do a lot of modeling to simulate how this happens. But this is a very interesting science. But what's the big deal? Where's the applications? So I'll show you one application. Why people use sandbags to stop bullets and blasts. If you think about how each grain fails, in the granular materials, load transmits through the granular material through specific chain of loading. some of the grains we can never get loaded. They always pick the strongest resistance to go through. So the experiments show that if one grain is going to fail, it will explode. It will disappear. So you're going to missing one link in one of the chains. Then it takes time for the chain to readjust, find the neighboring load to pass. That means the very high, strong shock can only propagate inside the sandbags near particle wave speed, near particle velocity, never been a shock wave velocity. So that's how sandbags isolate shocks. So the two-particle science, you think back, that's actually answered. Everybody has been using sandbag. You know how that works. That's a very good scientific explanation. And of course, there are others. We have, from that result, we proposed a new concept to APAR-E that they want to make impact-safe battery packs for cars. So right now, the batteries in the cars are protected like a baby. And we propose, hey, this is not where you do this. The batteries is only part of the structure. What you need to protect is people inside. So make the batteries as gravels. And you put in front and back of the cars. Let them take the hit. Then you're gonna protect the people inside. You're gonna cut the weight down. And for that concept, we just awarded $500,000 for next year. And hopefully we're gonna continue on that. So once we understand some basic science, there's quite a bit of applications you can expand out. Yeah, this is another science issue that we haven't understand. This is a very brittle material. We have a beam of just a sample, tensile sample of a single crystal silicon, but it's very thin. So if you have brittle materials, if you want to break it, in tension, how many pieces you're gonna expect that's gonna break?
3.
2, maybe 3, right? So that's the common sense you can have. Think how many pieces this thing's gonna break. It's a brittle material, and I'm not gonna pull it in tension. That this is just holding place. I'm gonna pull it. This is on a high-speed camera. So I asked the student to bring me the fracture surfaces to look. And the student said, there's no fracture surface. I said, no, what are you talking about? I spent a lot of money to make these samples. I need to look at fracture surface. So we bring this in on the X-ray, see a much higher resolution. But still, we actually, from mechanics point of view, we still don't know how to explain this. Under a brittle material, under very simple loading, under tension, why it explode to so many pieces? And it's repeatable. You take the whole thing to X-ray lab, it still explode. And it becomes very, very small pieces. This is an interesting experiment. We're pulling out a fiber. This is a 12-micron Kevlar fiber from the epoxy base. If you're in the composite field, many people are looking at how much force it takes to pull one fiber out of the composite material. Nobody ever seen the interface, how the fiber actually get pulled out from the matrix material. And this is the first time you can see it, how the interface forms. You can actually increase the contrast of the images. And we have the loading histories, so there will be quite a bit of an analysis you can do behind this. This is the example I'm going to show you that the power of this phase contrast imaging X-ray technique. This is a joint between a bone and a tendon. And we're pulling apart the interface at high rate. Then you see that the detailed features shows up in the tendon. In the regular X-ray radiogram, you're going to see the bone that's in dark, and the rest of it is a cloud. We see a lot of features inside tendon, how they got pulled away from the interface. What's the procedure? Where to break first? The only problem is that we don't know how to explain what we saw. So we have this new experiment technique, and we see quite a few things from different angles, and no one ever seen those before. So you don't see a tendon got pulled off the bone, and you see the damage image formation process inside the tendon at high speed. So I'm still looking for people to collaborate with that explain how that happens. We have different results on old tendons, young tendons. And recently, one of the college's preeminent faculty team, we're going to work on the explosive materials, energetic materials. So this is a safety for the energetic materials. We have simulants of the energetic materials that's got punched into by a sharp object, and we can characterize the deformation field around the punch. So that's one effort we start building to characterizing high rate response of energetic materials. All right, so that's the more recent fun we've been having. We're using this X-ray to see anything inside that's breaking up. Some of them we can explain, quite a lot of them we cannot explain because this is a very different angle. So what's the future? We plan, one thing is to further develop this in situ damage monitoring technique, so we can look at more materials. Currently, I have 3 projects in this area that we're supported to work towards the failure behavior of different things. So we're going to accumulate more experiment results. We put different materials into it on the X-ray. We can see much more from it. Then we can develop damage models at different scales. We can focus in a very small area, like the fiber got pulled out, or in a bigger area, you have to see the grain interactions inside an energetic material, for example. The second area, we're going to focus more on the energetic materials. That's aligned with the formation of this preeminent college faculty team. So we currently have 2 programs. One's actually just kicked off today, sponsored by Air Force Research Lab. Dr. Martin here is a sponsor, actually. We had a kickoff meeting this morning. Then I have another, as a portion of a Center for Shockwave Processing of Advanced Reactive Materials. This is a collaboration with Notre Dame that Steve Sun and I were a member of that team. So we will fund it for at least next 5 years to look into how shockwave interact with energetic materials. So we want to further develop capabilities to explore the dynamic behavior of energetic materials. And that's, as feedback from the Air Force, that's a fairly fundable area and should be interesting. It's less explored. Then the last area, there's a lot of handout problems in the penetration behavior. My first research sponsor is a top expert in penetration mechanics. And eventually, I think I was gradually influenced. So I'm looking more into the penetration issues. So we have a few programs now actually funded to do this, to predict the ballistic limit, to look at the penetration behavior. But the one aspect that we actually worked on the project a few years ago, supported by DTRA, Defense Threat Reduction Agency. We spent a couple $1 million to develop instrumentation that we can embed inside the targets. So we can modernize ballistic impact experiments with much more output from one experiment. We can put sensors in the very different places to understand the event much better. And of course now with X-ray. So that's the one area I plan to develop, and would seek funding in those areas when I have an opportunity. So now to summarize. This is more than 7 years ago. I've been very fortunate that I have a first-class education all along my life. Have the fortunate to work with very smart people, very hardworking students, and also I've been very fortunate to have sponsors that let me play in this area, in a very narrow area, continuously. So I've been on this topic nonstop over the last 25 years. Actually, when I started when I was a graduate student. And we're still working in this area, and I'm still fairly well funded. So always consider myself as a very fortunate person, very lucky in that position. So early stages, we develop techniques to make sure we characterize the impact response materials properly. And we summarize most of the work in the form of a book. And recently, we opened up basically a new channel. Even we repeat the historical dynamic experiments. Now we can see what's happening inside. So that would produce a lot more insight into physical modeling of those events. And in the future, I'm still aiming at major challenges in the field. You also always need to keep a few problems in your mind that would keep you thinking. Sometimes you even forget eating. That must be there. So I don't know if I can solve them, but these are the things in my mind. I want to do it. Yeah. So that's the last slide. Actually, my materials head is not here. I'm a 2/3 aero professor, 1/3 materials professor. So my materials boss told me that his logo should be half of the aero logo size. So thank you very much.
I'm sure Wayne will be happy to answer your questions. Please.
I have a question on the Xray Diagnostics. What's the typical duration of the Xray being passed, and what's the energy level?
The energy level is adjustable. So you make the undulated gap small, you generate very high power X-ray. Yeah, so I think the one we use is the 19 keV that we're typically using. For the duration, it's continuous. It's just that it's a big storage ring of the electrons that running around. Every 3.6 microsecond, there's one burst of very bright electrons coming out. So our camera is face locked with that ring. Every 3.6 microsecond, you make sure the camera aperture is open. But you can also use a more continuous way. There's 24 different small bunches within that 3.6 microsecond. So they can coming out, and it's continuous 24 hours.
Okay. So for the X-ray image, it's 2D or 3D? Because in reality, it's 3D impact.
The image is 2D. In the slow static experiments, you can do 3D. Basically, if you load the sample and you're going to rotate the sample, you take X-ray images at every angle. Then you do reconstruction. It's called tomography. So you see 3D images. At high speed, you cannot take things that many angles. You can try a few angles, but not many. So 3D is still a challenge. We're actually working on it. Yeah, I had trying to get one of my PhD students working on that topic, but still need to find a sponsor. We accumulated these results over the last year. So this is about time I'm actually need to travel around and to sell to program managers. Hey, I have this nice capability. Look at this. I can look at your problem. So this is what actually what I'm start doing. But that's a very important area that I want to see high rate 3D images. And also on the material side, I'm building up a high rate X-ray diffraction capability. As the phase changing at very high rate, trying to record it in X-ray diffraction.
So if you have a stainless steel Kolsky bar and you put a stainless steel sample in the specimen, I wouldn't expect that you'll get the perfect transmission. Like you got losses because of the interfaces.
If you make the interface carefully,
You don't get a reflection.
you have one bar. right?
It's
So
continuous, but if I have
yeah, so that's the whole trick. So the whole trick, your sample has a small diameter, then it's going to get crushed. But that sample has the same hardness as your bar ends. The bar ends is going to deform, so you actually need to harden the bar ends.
Yes.
So when you had the silicon carbide sample, then you had a silicon carbide end on your bar? Is that what you just said?
With the silicon carbide sample, I use the tungsten carbide Platens, and the tungsten carbide Platens also radially confined. So I either use a metal ring heated up, then let it cool down to shrink on the tungsten carbide, or use shape memory alloy. Initially let it expand, you heat it up, it shrink in. So for the silicon carbide sample, if you just have a tungsten carbide Platens, it's going to break the Platens as well. Yeah, so these are some of the challenges. Some of my samples are much harder than the platinum material. So you need to put things in between that will protect your bar and also make sure the sample deforms uniformly, the no stress concentration, and also not affecting the wave propagation. The impedance of all the Platens need to match along the way, along the bar. Yeah, so some of the hard materials have this challenge that if you don't do carefully, the sample end up inside the bar. It's much, much harder than the steel rods I'm using is the hardest steel you can find. It has a tensile strength of 2.5 gigapascals. But even that, the ceramic samples can easily indent into the end of the bars.
Do you put any of your effort into deriving constitutive relationships from your measurements? So instead, not just looking at what the materials do, you can get an idea of the response, so one can do modeling of bigger structures and more complicated things than you can do in your laboratory?
We haven't been emphasized on that side. We typically work with a bigger team. The modelers typically on the defense lab side. Yeah, but now we have got a lot more information. I'm not sure if the traditional modeling method is going to work with all the information we observe from inside sample. So actually one of the items I list there, we're going to develop modeling capability for the stuff we observe. There's going to be multi-scale modeling.
There are statistical damage models that could be calibrated by this sort of measurement.
Yeah, yes. Some of the people are working on this. One guy at UCLA, I was actually talked to him a known time, trying to use, from the image itself, develop statistical models to model the damage.
Is there an equivalent to the Polsky bar for tensile testing?
Yes, we have Kolsky bars in compression, in tension, in torsion, in multiple axial compression.
So they use for all.
Yeah. So I probably have the most bars in collection in any professor's lab you can find in this country.
When do you plan, or are you planning to get back into airships?
Maybe. It's if I can find time. These airships you ride on it, especially in the early morning, you have an irresistible tendency trying to get up on there again. When early in the morning, you get up there, get in the clouds, just below the cloud, shut off the engine. It's so quiet, you look down, you feel the earth breathing. That's, as an aviator, you cannot resist that feeling. You want to just get up there. But it takes time, and I don't have access to this now. But if I have a chance, I will.
Wayne, let's thank Wayne one more time.